Good evening. So, I want to talk about a couple things. I know I talked about process being the most important thing in this class, not the actual answers. And I want to reiterate this. I want to reiterate this for a couple of reasons. Well, they'll become obvious, hopefully, for those of you who understand this. If you just are worried about the answers, what's going to happen is you're going to get out into the real world and you're not going to know how to solve the problems that they're going to be assigning to you, which is fine because you can look them up. But you're going to be slower and you're not going to be as engaged to be able to be basically be a leader. And what will happen is, right, you could be perfectly successful. There's nothing wrong with it. But realize you're making a choice that those who become good thinkers, those who learn the process, whatever they're doing, whether it's stocking shelves at a grocery store or a big box store, or whether it's programming something, or whether it's running a company or a department in a larger company, or owning your own company, that if you understand the process that's going on, you're going to be able to be successful in almost everything that you do. So I continually want to push process. That's so important to be able to understand the process, because when you understand the process, here's an example. And this goes from way back. At one point, I learned how to take pictures. And I did it on an old camera before. Actually, it really wasn't digital cameras. There were some, but they weren't very good. This is many years ago. But there's a bunch of different things that you can change on. You can change shutter speed, f-stop, and what's the third one? Aperture. And so you can change those things, and you can also change things like the size of your camera and the film that you use and things like that. But when you understand the process, what each thing does and how it works, it allows you to take better pictures because you know which things you can fiddle with and when. And the same thing is true in this, right? I don't care. It doesn't matter that you know how to turn no, it really doesn't matter, right? Because you can go and look it up if you want to take, say, a number, a decimal number, and turn it into a 2's complement binary number. Literally anybody can look it up that can spell reasonably well and understands at least the concept of it, can look it up on a website. No problem. So that's not a skill that's important, but it is important to understand that way of thinking. Being able to come up with that way of thinking, because whenever it is, right, and it's a matter of being able to think through the problems. And here's the thing, and it's really important, I think, for people who are 18, 19, 20 years old right now, you don't understand things. You don't understand. Let me back up, because I don't want to try to throw you under the bus, because it's not true. It's in most workplaces, especially when it comes to intellectual products like programming, 90% of the work is done by 10% of the people. This is pretty much true across the board. I don't know if the numbers are exactly that, but that's what I've heard before. 90% of the work is done by 10% of the people. Those people are very highly sought after, and they're also really well paid. So if you're worried about getting well paid, or you're worried about being sought after, both of which that probably means better pay, or better benefits, or better whatever, right? You might be able to work fewer hours a week, or you might be able to get more vacation time or whatever it is, right? Because you can be more productive in the hours that you're there. So part of that's part of that is learning the process. And so that's why I want to push on the process. The other thing is, and this is new in some ways, because when my generation was 20 years old, we were not very smart. We just weren't. And we didn't have these little things in our hands that we could pick up and type in any question and it'd give us the answer. We would have called that an encyclopedia, which was in the library, or maybe you had one, a set of it at home. But now you literally can look up anything that you want to know. However, the problem is, there is a problem, there's a price to pay for that, is that your attention spans, now maybe not each one of you, but a lot of people's attention spans in your generation is very, very short. Some people, maybe you know some of them, 15 seconds. That's it. They can concentrate on something for 15 seconds. Because that's how long a TikTok video is. Or now the YouTube Shorts. Not to say those are bad things. They're not. The problem is, though, is that you're not able to concentrate on things. I don't think I was good at concentrating on things when I was 20 either. But learn how to be good at that so that you can concentrate and solve problems in the long run. It will make you a better thinker. It will make you a more complete person, and it will make you more employable. And I think that's so important. Not just for this class, but for life in general. So that's my pitch for the day. I probably should have led off with, I've gotten 4 graded. I haven't finished grading the exam yet. Still working on it. When it comes out, it's going to come out in whole. So I don't want to grade one person's or another person's. I'm going to grade them kind of across the board. And so grading has proved difficult for me because because everything's online. And so I'm not used to that. And so I'm not, because I can usually put better notes on things with my pen. And I can't do that now because I don't have a physical copy. Of course, I could print it and that kind of stuff. But I don't know that probably would be worthwhile for any of us. So it's taking a little bit longer, and my process isn't as good. I'm working on trying to get it better. Okay. And assignment 5 just came out today, so that'll be due on Friday. Okay. Doesn't matter. Okay. All right. So the other thing I want to do, actually, is I realized that I didn't do K-maps correctly. So I want to show you a K-map, and we might as well do the one that's in the book that we did for the assignment. And I think most of you figured it out, but I want to do it correctly so that you all see how to do it correctly again. Okay, so we're gonna go ahead and do this K-map. Now, one of the things I want to point out is what we've got is, I'm going to say that W is in the first position, then X, and then Y, and then Z. And I was going through and looking at this. Man, all those things look a lot alike, especially when you're writing them down and looking away and looking back and looking away and looking back. So what I'm going to do is I'm going to actually create all of them into a binary number. It'll make it easier for me. What I mean by that is if W is prime, I'm going to give it a 0. If X is prime, I'm going to give it a 0. If Y is prime, I'm going to give it a 0. And Z is prime, I'm going to give it a 0. If it's a 1, if it's positive, I'm going to give it a value of 1. And what that will do is that will allow me to more easily look at these and think about them. Okay, so this is the order that I'm going to put them in because it's alphabetical. And so I'm going to look at these numbers. So I'm going to say the first one is 0, 0, 0, 0. I don't need to do a plus. I can just do a comma, I guess. And then I should see a 0, 0, 1, 0. And then a 0, 1, 0, 1. and then a 0, 1, 1, 1, and then a 0, 1, 1, 0, and then a 1, 1, 0, 1, then a 1, 1, 1, and finally a 1, 0, 0, 0. 1, 2, 3, 4, 5, 6, 7, 8, and that's how many there are in the problem. So it looks like I've gotten it correct. Okay, so, come on. Where are you at here? Okay, so I'm going to put the WX on this side, and the Y and Z on this side. Now, it turns out that it really doesn't make any difference how you combine these. You can do it however you want. But this next part is really important, and this is where I made the mistake. So I started out with a 0, 0. This represents W naught, X naught. We'll go 0, 0 here. And then I'm going to change one of them. Actually, here's the interesting part. That's actually pretty cool. It doesn't matter which one you change. I usually am always going to change this one. I'm going to do it in this order here. It's kind of the traditional order is to change the second one. And then on my next step, I'm going to change one of them again so that I get a new one. So I get 1, 1. And this is where I made the mistake. That's exactly the spot where I made the mistake. I actually put the 1, 0 here. And that actually makes a mistake on it. Let me finish this and then I'll talk about me making a mistake and how that works. Okay. So I'm going to do the same thing up here. And then finally I'm going to go like this. And also notice that the end one here this 1, 0 is exactly one character. It's exactly one character away from 0, 0. Right? I can change one character. Which means that if I find a pair on the back side here and the front side, so there's this one and this one, I can actually pair those together because I'm going to assume that they wrap. And so I'm going to wrap top to bottom and right to left, which means, right, that if I go off the right side, I can come over here and grab this side, and if I get down to the bottom, I can come around to the top again. Okay, and that'll come in a second. All right, now let me take a pause here. I'm going to talk about what happens when the instructor gets something wrong, because I did. So first off, I am not the professor who thinks that I know everything or that I'm always right, because I make mistakes just like you. I'm human, so are you. I apologize for it. It sucks. Bummer. Most of you actually went out and found out, hey, you were confused by this, and she went and looked some other things up, I'm guessing, and you figured it out. And some of you stuck dogmatically to what I had to say, and you pushed through it. I didn't mark off anything if you did the grid incorrectly, but then if you weren't able to model the grid to the Booleans, every single person who modeled it, who had things in the other order that I originally had it in, made a mistake when they translated their grid into Boolean. Every single one. So just be aware, right, that if it looks confusing, let that red flag go up. It's okay. Because I am not somebody, like I said, I'm not somebody who thinks that I'm always right no matter what. I can be proven wrong, and I actually challenge every single one of you to prove me wrong. I'm happy to have you do that. The book can be wrong too, by the way. And in fact, there might be a case or two where I will disagree with the book. Although I don't know that I've ran into it just yet. Okay. So what I'm going to do is I'm going to go through here and I'm just going to put ones at all of the places that are in our set. Okay, 0, 0, 0, that goes here, 0, 0, 0, 0. Okay, so 0, 0, 1, 0, so that'll be here. 0, 1, 0, 1, 0, 1, 0, 1 there. 0, 1, 1, 1, there. 0, 1, 1, 0, there. 1101, 1101, 1111, and 1000 here. Okay, so what I'm going to do is I'm going to look at these, and I'm going to say, aha, look at this. There's 4 there. I could go this way with this, but I also could go this way. And with this one, right, I could go this way, or I could go this way. But this one only has 1 match here, and this one has... I always want to put things into biggest group as possible, because the bigger group I can put it in, then I can reduce the number of variables when I get done. I'll explain that in a second. So I'm going to go this way and this way, although I would have been happy to accept any other combinations. This is just going to be the fewest number of them. Okay, so what I can do then is anytime you have 4, then however many total variables there are, in this case there's 4, because there are 4 in a group, that means I can reduce it by 2. So I only need now 2 variables. And so which 2 variables didn't change? Okay, so it's in the middle here. So the second one didn't change, so z. And here, w changed, but x didn't. So I can say x, z. That's my first one. And then I look over here, I'm going to do this one. I'm going to say, okay, now this one is 2. Okay, so 2 means I can take 1 away. I can take 1 variable away. And if I had a group of 1, I couldn't take any away. Okay, so this one, I look at it and I say, what didn't change? Okay, w doesn't change. W naught, because that's what it is, right? The 0 represents w naught. And then y, and then z naught. And then I go to this one, and I say, which one don't change? Well, z did not change, and neither did x. And neither did y, right? So it's x, and x is a 0 the whole time, and y is a 0 the whole time, and z is a 0 the whole time. So that gives us our last term. Okay. Good. All right, I'd ask if there are questions, but there's only one other person in here. So, but if you do have a question, feel free to put it in. And I can't even see who's watching it live. And I don't pay attention to who's actually watching it and who's not, because honestly, if you don't want to watch it, not my problem. Okay. All right, so I want to also talk about number 2, because I think some people got confused about that one as well. And so I want to do that, and let me open that up here. Okay, so that gives us, that's the one that gave us, let me bring it over so you all can see it. So this is the one that gives us that table, and we've got these X's in there. I don't know, that doesn't make sense. Okay, all right, well, the X's are don't care. That means we could include them, we could not include them. It doesn't make a difference. It's not, usually it's a case where it's not possible for those results to happen. So we don't care if we include them in our Boolean expression. Okay. So I like to do it this, like, what do they call it? Vertically. So I like to go like this. Although a lot of you did it the other way. And that's okay too. 0, 0, 0, 1. And to correct myself again, 1, 1, and 1, 0. And this side is the X, Y. Okay. So the first one here is big X. The second one is also a big X. Then we get a 1, and then a 0. And we jump down to the bottom, we get a 0, and a 1, Is that right? Yep. And then here we get a 0 and a 1. All right, so now let's start grouping. We could group the two x's together, but since we don't care about them, we don't have to include them, so we wouldn't. Fair enough. But I see that there's a pair of 1s right next to each other here. And because I want to create the biggest groups as I can, right? But it has to be a square. And so, which means I could include these two and these two, right? Because they wrap, remember? So this actually sits on top there. So that, but this one's a 0, so I can't do that. So I can do this one right here. So then I look and I say, okay, well, which one first? So let's do this one first. So this one, what doesn't change? X doesn't change, and Z doesn't change. Then I look here. X naught doesn't change, and Z naught, Y changes. In both cases, Y was the one that changed. Actually, so some people answered this. And they put a bar over the top. This is wrong. I'll show you why. Because when you put the bar over the whole thing, it means you and them first, and then you create a bar. And then you flip it. Okay? So that's like saying this. X, Z, naught. Are these two equal? Well, let's do De Morgan's rule on the right-hand side. Oops. On the right-hand side. So let him figure it out. So we do De Morgan's law. So that says negate the whole thing, so we get X naught. Then we flip the sign from an and to an or. And we get not equal. Because they're not the same. Okay. And I want to talk a little bit about also the last two problems on this one, which were the null labor flip-flop, the NL flip-flop. And the NL flip-flop says if n is 0, don't change the state that it's currently in. If n is 1, change the state to whatever L is. Okay. So let's draw a diagram. And I think most people did this. But some people missed that when I was describing that, I have an n and an L variable, but I also have whatever the state of the flip-flop is in. And that's formally known as Q of n. So then I can have a Q of n plus 1, and this will be what it changes to. Okay. So let's just do our truth table. And just get them all in there. It wouldn't matter a bit of which order I did them in. Oops, I missed one. What did I miss? Oh, 0, 0, 0. All right, well, let me fix this because it will drive me nuts if I don't do it right. Let me rephrase that. It'll be driving me more crazy. I'm already crazy enough. I don't need to be more crazy. Okay, so let's look at this. If n is 0, what happens to this state at the end? Doesn't change. Just put them in the zeros. Boom, 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 boom. I don't have to do anything. No. Oh, no. What did I just do? I just said, it says it doesn't change. So it's just whatever q of n is. So this will be a 1. If this is a 1, then we just copy over the L. Okay. Good. There's my table. Okay. So then I have to create these gates. So here's the interesting part. I can just draw a box like this. And I can call this S. And these R. And this Q. And this Q prime. So then what I need to do is I need to say under what conditions should I push the S button and under what conditions should I push the R button. Now remember, one of the things that's cool about a flip-flop is if you just push in zeros, it doesn't change. Right? This is set and this is reset. That's what the R and the S stand for. So if I give the set to 0 and the reset a 0, it will never turn off and it'll never turn on. Okay. I don't have to worry about a clock because we're not talking about a clocked one here. So I have an N here and an L. Under what conditions should we set it? Because remember, if we give it 2 zeros, it'll just be happy to just stay in the state it's in. Okay, so it stays in the state it's in. There, and there, and there. But actually, it turns out that I don't need this one. But I'll explain in a second. So I just want to look at these top two. What I can do is I can actually push these two together. Well, okay, wait. Yeah. If I want to set this, I can just AND these two together, and that will set that. So if I take this one and push it through an AND gate, then both of them have to be on in order to turn on out here. So the Q of n plus 1 will turn on then. And if I do an N, N is on, L is off. Now I want to reset this. I want to turn this off. So the top one is these two. Okay, so these top two here, it doesn't change anything. It just keeps the state it's in. So we could say all 4 of these are keeping in the same state. And so is this one. And so is the bottom one. We don't care about those. So, but we do care about this one here. And we need to make sure that this one gets turned off. So that's the only time that the state is changing. And that's one of the things that's great about a flip-flop, right? Is it doesn't change if you don't give it inputs. So in this case, Will either of these two lines be positive? And the answer is no. How about in the second case? No. Third case? No. No. Okay. Here. No. Here. Oh, wait. Actually, that's not true. In this case, the reset will be fired. So the reset will be on here. Oh, okay. That's nice. Because we want to turn it off anyways. We don't care if we override that. That's all right. So then here, we see that the reset's going to be on. So both of these are going to just turn it off. And then we look at the bottom two rows, and we see that the top one will fire, which means we want to set, and which means it's turn it on. Okay. Spent a lot of time talking about that, but that's okay. It's good to go over some of these things. Okay. All right. Now what I want to do is I didn't talk about something. What's the best way to do this? I think the best way to do it is to go back to our Marie code. I'm going to bring up one that's a little bit more complicated this time. Now, I'm assembling this. Now notice here, first off there's these comments, so it ignores those, so it starts out at clear. But this is A, so can we figure out what that is? All right, so what's this in binary? That's this. Oh wait, no. This one's 8. And 2, and 0, that's A, and then 0, which is this. So that's what it is in binary. Here's the advantage. So this is called machine code. So the difference between assembly language, which is what we're looking at just a second ago on that website, this is assembly language. It goes line for line and it changes it into machine code. In this case, Marie allows for blank lines and it allows for comments in the code, which are then skipped when we assemble it and turn it into machine code. Oh, actually, I messed up, didn't I? That was a mistake. I only did the first half. There are 8 more zeros here. So then we look at this one. So, okay, so then what we need to do is we need to figure out some things and kind of look at some stuff. So we say store. And so remember in Marie, only in the hex code, remember there's only 8, right? There's only 8 commands that we could possibly use. So the 8 commands are 101. That's clear. This is 001, store. This would be 011, input. Then we go back and we see this one. Oh, look at that. It's back again. So we'll continually see the first 3 bits are the opcode. Let me spell that. Opcode. It's one word. What it means is the operation that we're going to do. The code for the operation. And this is operand. because the operand, in this case actually, plus 6 plus 8 zeros. So this is going to be 8, 9, 10, 11, 12, 13. 13 bits in Marie. And this is 3 bits. Because each position has 16 bits to it. Right? Which is 2 bytes. All right, so that's a lot of that was all review, but so let's actually now talk a little bit about the next, going into the next chapter. And the next chapter is about instruction set architectures, or ISAs. Architecture, otherwise known as ISA. Now, there's some considerations to be had with ISAs, with the ISA. So our instruction set is terribly small. It's very small. It's only 8 different instructions. In fact, it's probably too small for practical use. It depends. Maybe we could use it. There's some applications where we could use it. But because it's so small, it doesn't take much space, which gives us more room for operand. Which means we've got more registers now. That's nice. We've got 2 to the 13th. 2 to the 13th registers, which is about 8,000. It's more than that, but it's close enough. Well, 8,000 registers. Boy, that's a lot of memory. Remember, we can trade memory for speed. We can always do that. So that helps us. We can run faster because there's more memory. Also, no. Okay. I was going to say also it's faster to decode this, but it turns out actually it's not once I thought about it for a second. So it isn't faster to decode the first 3, the opcode. Wouldn't matter, because we do it in parallel, so it doesn't make a difference. Okay. So, but that actually is true, that the smaller the opcode, the faster we can the higher the speed is that we can push through the processor. We can go through faster because the opcode is small. That actually is, there is truth in that. Because our clock, this is where it gets cool. Because everything is simple, in this case we only have 8, our clock has to be at the speed that it is. It has to be at least as slow as the slowest operation. The more operations there are, the more complicated they become. The more complicated they become, the the higher the clock speed, or the longer between ticks, between motions, between steps. There's some ways, we'll talk about them, but there are some ways to speed that up. That's the reason why it's going to be faster, because the more complicated things are going to take longer. Okay. Also gives us an advantage of more operands. The problem is, because there's so few, sometimes we have to do many steps to do some of the things that are more complicated. So some of the things that you can do in one step, if you had a larger number of instructions in your instruction set, because it's going to be more complicated, you could do it in one step. Instead, it's going to take 3 or 4 or 5, maybe as many as 10. I don't know. So that's a big deal. Okay. So instruction sets. So we'll get into some examples as well. It is possible for the instruction set to actually change in size. So that, like, if our first 3 here, say we decided to use our first 3 here, and if they were all 1s, then instead of putting that as whatever it is in the all 1s position, we would say, okay, if you see 3 1s, that means do 3 more. Then the next 3 are also opcodes. And so in a lot of ways, that's going to work like UTF-8. We talked about it briefly. UTF-8, right? It's as if it's a way to do letters. It will be an ASCII character all of the time, unless a certain sentinel happens, in which case then automatically we know that it's not ASCII, and that we'll kick it over, and then it'll tell us how many. And so instead of giving us an instruction there, it'll tell us how many more bits to look at to figure out how big our to figure out what our character is. Right, because we could go to Unicode, right, which goes to two bytes instead of 1. Okay. Okay, so notice here that there's 2 bits together, right? And so remember, what was this? This was A 0 0 0. And each one of these is a byte. There's multiple ways to store this, and this gets interesting. So let's say everything's in addresses like this. So I could store it like this. Right, this position 0, that's position 1. This is what's called little endian. Not to be confused with little Indian, which is a completely different thing. And the other way to do this... Oh, wait, I actually messed that up, didn't I? Yep, I did. Yep. Wait. Nope. This one is not Little Indian. This is actually Big Indian. Because the bite, this one has more significance, right? Because it's to the left, right? It's more significant than the second one. And so it comes first. And the other way to do this is like this. We say 0, and we have 1, and this is Little Indian. And supposedly, these come from Gulliver's Travels, a book called Gulliver's Travels, and that is there's two different tribes on some island he lands on, and the tribes are fighting over how they end their stuff. You'd have to go and look it up, or read the book, or maybe you have read the book. I think I watched a television show on it a long time ago. But I do remember it was an enjoyable story, so fair enough. So, Little Indian says the least significant bite is in the first spot. The more significant bite is in the second spot. Now, so it's important to note how this gets stored. And can we look at Marie and tell what Marie does? What does Marie do? Is this Little Indian or Big Indian? We don't know. Why don't we know? Because each of these is addressed based on the full word, not based on a byte. So if you're storing a full word in each cell, in each address, well then you can't do Indian, right? Indian doesn't matter. So Indian only comes into play if you're doing byte addressing. So each byte, or 2 hex characters, has its own address. If this was still done in this order here, it would be Big Indian. So that's important. And Big Indian is actually easier to read, generally speaking. If you're reading opcodes like this. I don't know why you would do that, but maybe. But here's the thought is that if you looked at Little Indian and you decoded it and you spent maybe about a half an hour to an hour, it might take you a little longer than that. Pretty soon you wouldn't even think about it. You would just automatically be able to see it backwards. Just automatically, it would just happen. It's pretty cool that way. It's interesting activity. If you want to teach yourself to read upside down, some people are really good at it. Some people are not. But if you can teach yourself to write upside down. It's actually not hard. Pick up a book, flip it upside down, and read the whole book upside down. If you do that, your brain will get faster and better at reading upside down. And and it will stick with you for the rest of your life. I know this from personal experience. I made a decision when I was young, actually quite young, younger than you guys are now. I was probably in late middle school. And I said, when I sit across from somebody at their desk and they have a paper and it's upside down to me, I want to be able to read it. Because I had a situation where I wanted to be able to read it and I couldn't. So I took a book, I flipped it upside down, and I read it, but I read it backwards. It's really interesting, right? Because normally you would flip a book, right? You would flip a book like this. Or maybe you guys are seeing that backwards. Let me get my camera open now. Is that backwards? I don't even know. So, wait. So that's my right hand. Yeah, so it's mirrored. Okay. So, oh, that's right. We did that so that you could read when I held something up. Okay. So, you flip the pages backwards. That was the hardest part. It was easier to figure out the text than it was to figure out the words. I should do some more practicing with that. That'd be kind of fun. Yeah, I'm not bizarre or anything. Trust me. We will have some questions about big Indian versus little Indian. Guaranteed. Okay. So there's this internal structure of the storage, and storage, remember, is registers. So there's 3 different types of ways to do this. One is stack architecture. Let me explain stack architecture. Actually, let me list out the second one here first, and that will help probably be able to define this. Accumulator architecture. Which one is Marie? It's accumulator architecture because there's one register for the for the kind of the active thing, the active digits, the active number, or the active bits. Sorry, active bits. That's probably the right word to say it. One register for active bits. Actually, I can actually active word, because that's what it is, right? It's always going to be a word. That's how the size of it. All right, so let's talk a little bit about stack architecture, because it's actually different, and it will lead us into our next idea. A stack architecture uses a stack. A stack, we could assume that it's infinitely big because we can fake it. A stack of registers. Because that's actually indeed what it can and will do. Let me list the third one here, and the third one is the general purpose. So this general purpose uses a set of general purpose. Oh boy, I didn't even spell this right. It uses a group of things like the accumulator, and so it uses multiple registers. Each one with its own name and its own way to do things. So, like in this case, we just have a single add because we only have one accumulator. We know that's where it is. But in a general purpose one, say if we had 8 different ones, we'd have to have a different add for each register. Or potentially add would always look at register A and register B. It would always just add those two values together. And then maybe store it in register C. And each instruction set can be different on how it does that. But they're going to be general purpose so that they're specifically... so we're going to load things into them. But the accumulator, we don't have to ever load anything into it because we always put something, every time we go through our cycle, we always are getting something new into the accumulator. And when we do an add, I just noticed a comment here by a student, and actually, I'm glad that I was able to go back and fix that for you. Okay, for the K-maps. Good. Let me think if I've ever used one. Actually, I want to tell you guys a quick story here. Let me take a pause here, and I'll talk about stack architecture because I think that's the one that makes it's a little bit difficult. Okay, general purpose. Yeah, I think I've covered that decently. Okay, so let me tell you something that happened today in my regular job. Okay. One of my coworkers had a problem. This happened this afternoon, sometime after lunch. And his code wasn't running. And so he couldn't get it to work. And we could look at the stack trace. Hopefully you guys know what a stack trace is, but that's different. Doesn't matter. And so I offered to help him because he's fairly inexperienced still. He's actually probably maybe... Let me think here. I think he would be classified as a junior, right? So because he's an intern. So I offered to help him out. He goes to Mankato, by the way, which is a good school. They have a Maverick program there that Thomson Reuters hires quite a few different programmers out of. So Okay, so I offered to help him try to work through it because he still struggles with that sometimes, especially since I know the code base a lot better than him. When we have thousands and probably in the tens of thousands of lines of code, so there's a lot of stuff there, and there's a lot of objects, and there's a lot of stuff going on, and so it's hard to kind of keep everything straight. I can't even keep it all in my head at the same time. And I've been doing this for about 2 years. And there's another guy who's been doing it for about 3 years, and he's in the same boat as me. He's like, I can. He knows some of it, but he doesn't know it all. But doesn't mean we can't dig into it and figure it out. Okay. So, anyways, I started helping this other guy, and we were looking at it, and it had to do with Chrome. He had updated his Chrome, and when we updated the Chrome, so on his a new version of Chrome came out, 106. And he updated his Chrome and on his computer. And then he updated the Chrome driver for Selenium, which is what we use. I'm not giving away any trade secrets here. That's how it always works. So, but the Selenium driver only works with 106 or higher. The problem is, I had 105 on my computer, so mine wouldn't work. So I had to fix that. Okay, I fixed it, and it worked then. Great. I was trying to simulate the problem on my computer to see if I could figure out what was going on. And there's a config file. It was saying that there was a config file that it couldn't recognize, or it wasn't saying that it couldn't recognize it, but it was saying that there's this thing called a routing. It was a variable called routing page. Routing page enabled. I think that's what it was. And we wanted that to be true. And it was, but it wasn't reading it in. It was erroring out. It's saying it didn't recognize the routing page. So, but then it would run and it would work just fine. And so when we looked in the code, there's a default value for that, which means if it kind of has a problem with reading in your text file, then it will automatically just give it a false value. Or no, I'm sorry, a true value. Okay, so that's great. So his tests were still running. And we searched for an hour trying to find that bug after I got mine to emulate the exact same thing as his. And it was getting some weird message that didn't make sense. There was other messages in there that weren't making a ton of sense. And then I re-looked back at the config file that he was using. And in the routing page enabled, the word enabled had 2 N's in it. We spent over an hour trying to debug what was going on his computer. And the problem is somebody had added a second N into the XML tag. Both the opening and closing one. So it didn't look like it was syntactically wrong. It wasn't. It's not syntactically wrong. But it needed to match exactly in order for the computer to recognize it. This is just, it happens. These kinds of things happen. And it took us an hour to figure out and change one letter. And here's the part. We were so stumped that we pulled in a third guy for about 10 minutes. And then we finally figured it out. So that's the kind of stories that are really kind of interesting if you're in the world of computer science, is that sometimes you will work a whole day and you will type one key on your keyboard. That kind of stuff does happen. Now, most of the time it's not the case. A lot of times there's more meetings than there needs to be, usually. Boy, we're moving along here. Okay, stack architecture. Okay, here's the thing. This is where it gets cool. Okay, so stack architecture. So imagine that it's that you have note cards, right? Hey, like these, right? And every time you do something, every time there's an operation, either it puts something on a note card and puts it on a stack like you would on your desk, or it takes the thing that's on top of the stack and it uses that and throws it away. It could also, take the thing off, use it, create a new card, put that card down, put that value down. Okay? So the way we talk about this is like this. What we can do, actually, let's go over and look here. This one has a lot. This one has a lot of stuff. So let me go to the addition one because it's much smaller. Go to the assemble here. Right, so we only have 7 things. So we're going to put those, we're going to put this one on top of the stack, then this one second, then this one, then this one, then this one, then this one, then this one. And we can actually just load them right into our stack immediately. So this is 7000. I'm going to pull this off to my other screen, and then I'll just going to draw them in. So 6000. 3007. 2008. 5000. There's a reason why I'm not actually saying these as if they were numbers, because they're not numbers, are they? 2007 and 5000. Okay. This is how it works. We can preload all of these things in the stack. Actually, it turns out that this won't work, and I'll show you here in a second. We evaluate this one as being input. Input. So in input, what I can do with the stack architecture is I can pull this out, I can recognize that this is an opcode and manipulate it as an opcode. And now in this case, we store that, if we look at Marie, we store that in X. But this is where it gets neat. And that's actually a memory location, right? We don't have to do that in a stack. In this case, actually, I'm only going to look at 1, 2, 3, 4, 5, 6, 7. Okay, that's right. Okay. Oh, that's right, because the X and the Y are zeros. Okay. So instead of this being a store X, I can just say store it on the stack. Okay, so I have a stack like this. So store it on the stack. So what value did I input? I'm going to input my favorite number, 42. Okay, and that'll be in binary, right? So that's, or in hex code, in hexadecimal, but whatever. I'm just gonna throw out that. Well, okay, that's still 42. That's still a hex code, right? 0042. Okay, which comes out to be a decimal number of something different. All right. So then, instead of storing X, we're not going to store it in X. We're just going to store it right in that register at the bottom of the stack, or sorry, the top of the stack, which in this case is the bottom because there's nothing on there. Okay. So then we do another input. Then this was store Y. But I'm not going to do a store Y. I'm going to do, so what's my opcode? So A0. Sure, A0. Okay. I'm just going to store it on top of the stack. So I don't need that extra memory. Now, I can do an add. Let's not use A0. Let's use 0A. So it's going to take this one and this one. It's going to add them together. What's A plus 2? C. What's 0 plus 4? 4. So, oh, but wait. Aha! This actually gets better. It takes them off there. They're gone out of the stack because we don't need to remember them anymore. Hopefully. In this case, we don't need to. And so then we put our 4C here on top of the stack. And this is output. So then we take this, pop it off the stack, and we print it. It's gone. And then maybe we would leave it there, maybe we wouldn't. We could have different ones, but that's just an example. And then this is halt. Or stop. So, that's an example of how a stack architecture would work. Here's the cool part. Because it knows these things are a little bit more complicated, right? This store, instead of storing X, I don't have to tell it to start in X, although I probably could. I could tell it to start in a specific spot. Instead, store it on the stack, because I'm going to use it in just a second. And so in that way, it's much easier to, it's going to be quicker. It takes less. Now this time it looks like it's the same number of steps, doesn't it? How about if input, instead of inputting it into some kind of an accumulator, which is what we assumed, didn't we? Instead, let's not store it in X. Let's say the input actually sticks it on top of the stack. In that case, that goes away. And that goes away because we don't have to store them. We can simply just we can do, now it's only 5 steps instead of 4. Input, add, output. And we probably would have to say something a little bit more nuanced than input. Maybe not. Input, put it on top of the stack. Input it, put it on top of the stack. Add the 2 top things on the stack together and put it back on the stack. Output. Take the thing on the stack, delete it, and print it. Halt. And I don't know, there might be a way to kind of make this go a little faster, but I'm not sure how it is. So the stack architecture is a little different. It is going to have a bunch of different registers. Not a bunch, I'm sorry. It has a stack of registers. And each one of them knows, each of the registers in the stack knows if it's full or not. This isn't actually true. Probably we keep a counter that counts how many are there. But that's a different story. We don't have to worry about that. That's how a stack architecture works. It's pretty dang cool, actually. But we're not going to deal with that anymore because that's not what Maria is. Marie. I keep saying that wrong. Fair enough. Okay. That's what I've got. I'm going to work on trying to get your guys' stuff graded. And process. Learn the process, boys and girls. Process. Learn the process. Because the process will better your life. And that includes every single part of your life. Now, you won't get it all figured out in your lifetime or mine. Or mine and yours, because there's a good chance that mine won't last as long as yours does. I hope that it doesn't. Because I hope all of you live very long lives. So, fair enough. Okay. Yeah, that's all I've got today. We'll pick up here and we'll talk about the next subject I have to talk about is Polish notation. Oh, wait, no. Can't do Polish notation correctly. You have to do it in reverse order, so it's reverse Polish notation. Which isn't, by the way, a slam at all. It's actually because the Polish were very, very good at mathematics. And they probably still are. So, but at the time, they were actually quite good when they came up with this. So it's actually really neat. Okay. That's where we'll start next time, is reverse Polish notation. And it's set up. Although, actually, I might have some things from the exam. So we'll see. Hopefully, I'm done grading by next time. All right. That's all I've got. I will talk to you all again nexter time, which in this case, all right. Thank you very much for that comment. That's a great comment because I did put it up and I think I forgot to link in the PDF for it, didn't I? Yep, Yeah, that's, yep. Okay, let me do that right now. I'm glad I looked there. PDF. Good. Add it in. Save and close. All right. Let me. Can I view as a student here? There it is. That should be there now. Excellent. All right, glad. Thanks for the question. Thanks for the question. And I usually don't acknowledge people because I don't know for sure if it's all right or not. Although most people can look in there and see who's actually doing the asking. But that takes a little more effort. So that's I don't I acknowledge. I would happily acknowledge you. So all right, that's good. We'll see you next time, and have a good couple days. All right, bye bye.